All right, so Assalamu alaikum. So today is going to be our 17th lecture, and that will deal with Brillouin zones. So in the previous lecture, which was uploaded, I hope you have a fair understanding of Bloch's theorem. Bloch's theorem tells us that in the presence of a periodic potential, as it exists in a periodic crystal, the wave functions for the free electrons, they are modified. Now, instead of having free electrons and traveling waves, we have a modulated free electron, which means that the eigenstates are now transformed thus. The Bloch theorem comes in different garbs, in different guises, and I enumerated about 3 different statements of Bloch's theorem in the previous lecture. So let me just recount 1 or 2 of them. So in its first form, which is the commonly stated form, is that the eigenstates for a Hamiltonian that includes a periodic potential is given in 1D by psi x eikx. This would be the eigenstate for a free electron, but now this plane wave is being modulated by another function ukx, which is periodic. And in order to account for this wave vector k, I put a small subscript here as well. This uk has a property that it respects the periodicity of the crystal. And furthermore, we also saw that the values of k, they are constrained by n pi uh, 2 pi over L. So this is the first form of the Bloch theorem. The eigenstates are modulated plane waves. If you would like to write this in 3 dimensions, I could write psi k as a function of the position vector r is given by ei k dotted with r uk function of r, where r is now a periodic function. If capital R is a lattice vector, then this relationship holds. So this is one form of the Bloch theorem. Another form of the Bloch theorem is that if I have 2 points, one is at x, the other is at a point A, and they are separated by a lattice vector, then the wave function at x plus a is going to be the wave function at the point A, but there is going to be a phase factor in between these points, which is IKA. And in 3D, this can be written as psi k small r e I k, but with capital R. Capital R is a lattice vector. And we also started off our previous lecture by deriving the Fourier decomposition of any periodic function. And we learned that any periodic function whatsoever, if rho r is the same as rho r plus capital R, and capital R is the period in space, then this function can be broken down in the following form. We can put a Fourier coefficient rho g, where g is a reciprocal lattice vector, e plus or minus I g dotted with r summed over all the values of g's, where g's are reciprocal lattice vectors. Okay, so these are vectors that live in the k space, but they're reciprocal lattice vectors, and we've already talked at length about reciprocal lattice vectors. So any periodic function can be written in the form that you just see in front of you on the screen. So this is what we covered in the previous lecture. So any questions about this? Unfortunately, we couldn't interact at all in the previous lecture, but so I'm open to any questions and any further deliberation on Block's theorem. And we're going to look at some really nice examples and really nice applications of Block's theorem now. So, but any questions about this, all this?
सर जो लास्ट लेक्चर की आपने वीडियो अपलोड की थी इट एंडेड वेयर वी प्रूफ वेयर वी गिव अ प्रूफ फॉर द फॉर्म 2 ऑफ ब्लॉक थ्योरम तो फॉर्म 3 जो थी उसका वहाँ पे प्रूफ नहीं था तो वाज इट डेलिबरेटली दैट वे या फिर आपने मिस
नहीं
कर दिया वो अपलोड करने में
नहीं, मैं अपलोड नहीं करूंगा। फॉर्म 3 का प्रूफ आप खुद कर सकते हैं। सो इफ यू एक्सप्रेस uk is a periodic function, this is a periodic function here. So what you could do is you could express uk as some ug, some bg, some coefficient bg, let's call it bg e plus I g dotted with r, and sum over all g's. Okay, so you could rather put this g as a, put g here as well, doesn't matter, and I put k here because you have to identify the k's as well. So you put this expression into here, eik dotted with r, sorry, dotted with r, ukr is now becomes this. I get b k g e I g dotted with r. This becomes b k g e I k plus g dotted with r. So this is the third form of Bloch's theorem. That's very simple, right? So I ended the video abruptly because I wanted to discuss the point that I covered uh, independently and interactively with you, because it's an important point and it also gives segue into what I'm going to discuss today, that is Brillouin zones. So don't worry about that video. It ended abruptly with a purpose.
ओके सर ठीक है
ठीक है, अच्छा अब हम चलते हैं. One thing that I would always like you to remember is that G vectors are distinct points in the K space. So if I'm just look at, I've talked about this, belabored this point quite a bit, but let me talk about it again. If I have a one-dimensional K space, and so we have all of these points K, and K's are given by multiples of 2 pi over L. So each of these spacings is equal to 2 pi over L. All of these are K points. Can anyone remind me why these K points are quantized? Where do we get this quantization from? Why
So
don't we
because
have a
uh,
finite G?
so the electrons are bounded in 3D space. Due to the boundary conditions, we get the quantization of k values.
Exactly. Confinement leads to quantization. Whenever you confine an electron inside some volume, then you'll have to apply certain periodic boundary conditions, and those boundary conditions lead to the quantization or digitization of the K space. And the reciprocal lattice vectors, the G's, these in one dimension are given by multiples of 2 pi over A, where A is the unit cell length in real space. So, of course, A is going to be much smaller than L. A could be nanometers and L could be the length of the solid. So, I take a big vector. This big vector could be 2 pi over A. And this is what G is. This is a reciprocal lattice vector. So, each reciprocal lattice vector G, the length of it contains many fine K points. The K points are, they outnumber the G points, and there is a very large number of K points inside a reciprocal lattice vector. In fact, you can find out the number of points. It's simply going to be equal to L over A, which is the number of unit cells inside the finite microscopic volume, and this can be a really large number, as you know. So G points are points inside the K space, but they correspond to the reciprocal lattice vector, and K points are finely spaced points inside the K space. So I hope this is all really clear to you. Now what we're going to do is, any more questions, by the way? Bakir, how is your work going, your independent study going? It's glad to see you today in class.
Say that. Yeah, I also want to talk about it after the class if you're available.
चलें ठीक है. All right, so let's talk a little bit about zones. But before we talk about zones, I would like to talk about the arbitrariness of K. Now, what do I mean by the arbitrariness of K? The arbitrariness of K means that different K points in the reciprocal space, the wave function at those K points for the Bloch electrons, as they are called, the wave functions that I've written above are called Bloch functions. Modulated plane waves are called Bloch functions. So Bloch functions are identical at different K values, which means different K values give you the same Bloch function, even though the energies could be different. So I'm going to talk about this arbitrariness of K. And how do I do that? So I look at the Bloch function psi K as a function of R. So please excuse me if I forget to put the arrow sign over K all the time, but assume it's always there. It's a three-dimensional vector. EIK dotted with R, AR. All right. But we also know that UKR is a periodic function. So I can express this in the following form. B, G, some vector K, E. Let's use the plus sign. You could use the plus or the minus sign. It doesn't matter because we're summing up over all G's. So this is the periodic decomposition of the function U. Okay. Now what we could do is the following. So I could multiply with minus I some G naught dotted with R. So if I do that, I could B K G E plus I G dotted with R E I G naught dotted with R. So what I've done is I've picked a particular reciprocal lattice vector G naught and uh, just decomposed unity into this phase factor and this phase factor and just threw it into the expression over. Okay. So now what I could write this as, this still remains psi kr. I could write this as EI k minus G naught dotted with R sum over all G's B K G E plus I G plus G naught dotted with R. Okay. So now what I could do, I could really replace this G plus G naught by some other vector G. I call it G prime. If I do that, the expression above becomes E I k minus G naught dotted with R B K G becomes equal to G prime minus G naught. This becomes E plus I. G plus G naught, I've already defined this to be G prime dotted with R. And now I can take the sum over G prime. Okay, because G naught is just a constant. All right, so now if I look at the expression over here, this thing, this is a Fourier coefficient which depends upon K, and it is computed at G prime minus G naught. So what I could rather do is I could, now K is a point in the reciprocal vector, K is a point in the reciprocal space, G is a point in the reciprocal space, and G naught is a point in the reciprocal space. All three of these vectors, K, which is fixed by the way in this expression, G prime, which is the variable of interest, the running variable of interest, because we're summing up over all G primes, and G naught, all three of these variables lie in the K space. They are vectors in the reciprocal space. So what I could do, I could replace this coefficient K with K minus G naught and put the vector G prime here. I'm at liberty to do so. So this is just a change of origin in the K space. Okay, so if I change my origin from K equals 0 to minus G naught, then I have to compute this Fourier coefficient at G prime. That's what I'm doing here. I'm just changing the origin here. So if I were to change this origin, I can easily do that. So I put E plus I J prime dotted with R back here. I sum up over all G primes. I have E I K minus G naught dotted with R. This is psi K. Now, if you look at the block form, this is just the block form. A plane wave. This is a plane wave in which K is now replaced by K minus G naught. And this is simply U at, now I can always change this G prime to G. Doesn't matter. So I can change this G prime back to G, back to G, back to G if I want, if I'm really interested. Doesn't matter, doesn't harm me. So this expression, which beneath which I put these brackets, these curly braces, becomes U. Instead of K, I have K minus G naught and R. This is how we've defined our U's. This is exactly the same fashion in which we define our U's. It's only that the variable K has now been replaced by K minus G naught. Hence, what this expression is telling us is that psi K at R, which is normally given by EIK dotted with R, being modulated by UK as a function of R, is exactly going to be identical to EIK minus G naught dotted with R, UK minus G naught dotted at R. A key expression here. And this G naught is a reciprocal lattice vector. So I can add any reciprocal lattice vector to K. I could add G naught, minus G naught, 2G naught, 3G naught, minus 3G naught, 100G naught, 500G naught, minus 60G naught. I can add any multiple of a reciprocal lattice vector to K. The block function isn't going to change. The function is going to remain the same. It's not going to change. So there is some arbitrariness in how we define K. When we look at the K space, the K space goes from 0 to plus a certain number and to a minus a certain number. In fact, it goes to plus minus infinity. The question of how many electrons are available to go into that K space is different, but the K space extends from minus infinity to plus infinity. Now, it turns out by what I've written over here is that we don't need to consider all of those k's. If we take a particular k point and another k point that is further away from that k point by some reciprocal lattice vector, the wave functions, the block functions are going to be identical at those points, right? So the you have to define, it's only worthwhile or only required to define k which is periodic modulo the reciprocal lattice vector. This means that if you're in 1D, your k needs to be defined only modulo 2 pi over a. Okay, so what does this mean? Let me give you uh, a practical manifestation of this. So, any questions? And I hope the example will clarify what I'm trying to say over here. Any questions?
So I have a question.
G.
सर हमारा जो जी नॉट वेक्टर है तो इट कैन ऑल्सो बी रिटन एज सम कम्बिनेशन ऑफ के वेक्टर्स, राइट?
हाँ जी.
क्योंकि वो सेम स्पेस में ही है, उसका बस लेंथ ज़्यादा है। तो इसमें हमने बस यही किया है कि वी हैव शिफ्टेड आवर पॉइंट ऑफ इंटरेस्ट फ्रॉम ओरिजिन टू सम वेक्टर जी नॉट। बाकी सारा फंक्शन उसी तरह का ही है।
जी बिल्कुल. इसका
ऑलराइट,
मतलब
ठीक
ये
है।
है, हाँ, इसका मतलब ये मैं अब आपको बताने जा रहा हूँ, ठीक है. So remember that G's are my nomenclature for reciprocal lattice vector and K's are arbitrary points. Okay, finer space points in the K space. Now, if you look at the dispersion relationship, let's draw the dispersion relationship. My K space. Okay, let me just draw a line here. So I'm going to talk about nearly free electrons, okay, in which those energy gaps exist. So this is K equals 0. This is some point pi over a. This is some point minus pi over a. These points are separated by 2 pi over a, which is a reciprocal lattice vector length. And I'm focusing on 1D for for convenience. Now we have other points. We have 2 pi over a, 3 pi over a, minus 2 pi over a, minus 3 pi over a. And let me just draw these visual guides here. All right. Now, if I were to draw the dispersion relationship for nearly free electrons, almost parabolic away from the zone boundaries, away from these plus minus pi a points, and then the energy takes a downward dip. And we proved that using the with the help of degenerate perturbation theory. So brush up your degenerate perturbation theory. Homework number 6 invokes your understanding of the degenerate perturbation theory. So please keep that thing in mind. On when you go beyond, when k goes beyond pi over a, the energy is actually higher than what it would be if there were no perturbation. So you start off from here, dip here. This is what the dispersion relationship looks like. Okay. This kind of diagram, a dispersion relationship which shows all the values of k from minus infinity to plus infinity and shows the energies. So on this axis, we have the energy as a function of k. This is showing zones. These zones are called Brillouin zones. Now you can pronounce these Brillouin zones in whatever fashion you like. You can call them Brillouin zones, Brillouin zones, Brillouin zones, whatever you prefer. Uh, so so these the K space is split up, is sectioned into Brillouin zones. Now we're looking at the convention that we starting our counting or zoning from the zero of the K space. So we have a symmetric arrangement of k points above and below 0, this regime here from minus pi by a to plus pi by a, this regime, sorry, all right, so this regime here from minus pi by a to plus pi by a is called the first Brillouin zone, FBZ, first Brillouin zone. These points pi by a and minus pi by a are called the zone boundaries. And we notice that energy gaps exist at the zone boundaries. All right. The zone boundaries to the left and the right, they are separated by a reciprocal lattice vector. Okay. Beyond pi by a, up till this point and this point, we have the second Brillouin zone. Between 2 pi a and 3 pi a and minus 2 pi a and 3 pi a, we have the third Brillouin zone. And the energy dispersion relationship goes out uh, goes out from minus infinity to plus infinity. Now the arbitrariness of k tells us that a wave function, say here, is going to be the same as the wave function here, right here, because these points are separated by a reciprocal lattice vector, and it's going to be the same as the wave function here, because pi by a and 3 pi a are also separated by a reciprocal lattice vector, and it's going to be the same as the wave function here. So what we could really do is we don't need to go out into the K space. We can bring all the dispersion relationships back into the first Brillouin zone. Everything can be defined within the first Brillouin zone, and still you can capture the entire drama, the entire dispersion relationship by putting everything into the first Brillouin zone, because the choice of K is arbitrary up to 2 pi over A. This diagram that I've drawn in front of you is one way of representing Brillouin zones, and it is called the extended zone scheme. But the arbitrariness gives us the liberty and the justification to just focus on the first Brillouin zone, because we can bring out all the parts that are further out in the second, third, fourth Brillouin zone, and we can translate them back into the first Brillouin zone if we translate them with with the proper magnitude, with some multiple of the reciprocal lattice vector. So if we were to do that, and I don't want to, let me just destroy this figure a little bit. So if I do that, if I take this string here and translate it backward by 2 pi over a, this will come over here. This string, when translated to the right by 2 pi over a by a reciprocal lattice vector, I will get this thing. This thing, if I translate by 3 pi over a, I will get here, and so on. So I can stitch back all the dispersion relationship curves that are further out in the higher Brillouin zone, and I can bring them back into the first Brillouin zone without any loss of physics, because the choice of k is arbitrary modulo 2 pi over a. So if I were to draw this new diagram, I just need to focus my attention on what's going to happen in the first Brillouin zone. All right, so see 0, pi by a, minus pi by a. So this is what the nearly free electron dispersion relationship is going to look like. sorry, हाथ जरा. And so on. So all the curves that are further out are brought back into the first Brillouin zone. All the action takes place in the stage that we call the first Brillouin zone. And there are gaps between these at the zone boundaries. These energy gaps appear, which we all know are proportional to this coefficient Vg, okay, which is the Fourier coefficient of of the potential function, okay, computed at the reciprocal lattice points. This kind of drawing is called the reduced zone scheme. So we had the extended zone scheme, one way of drawing the Brillouin zones. Now we have the reduced zone scheme. That's another way of drawing the Brillouin zones. And we can also do the following. Another technique is to take the reduced Brillouin zone and repeat it in all of K space. So this is what you could also do. Hmm. Uh, slightly. And so on. So you can take the reduced zone scheme and repeat it because of the arbitrariness of K. This is called the repeated zone scheme. So all three, the reduced, the extended, and the repeated zone scheme are valid ways of drawing Brillouin zones or expressing dispersion relationships. And each one of them has a utility of its own. So some zone scheme, some drawing methodology works better in one scenario. The other gives you more conceptual advantage in another scenario. So now what we have here, these points here. So if we consider the reduced zone scheme, we have a we have energy possible energy values that lie on this curve. Excuse me. And then another possibility of energy values. These strings, these possible energy values, they are generally called bands. This could be called the n equals 0 band, n equals 1 band, n equals 2 band, and so on. So I've introduced this new quantum number. I'll say why this is a quantum number, n. It's just like a principal quantum number. When we talk about the hydrogen atom, the K shell, L shell, M shell, each one of them is defined by a principal quantum number. This index is called a band index. And I'm going to invoke this further. Why do we have this band index? But now we have bands. The energy dispersion relationship is slotted into bands, and there are gaps between the bands normally. Okay, remember we're talking about a 1D right now, so there are gaps between these bands, and this is what is called the band structure of a solid. Now I'll talk about the band index, but before that, I'm happy to take some questions. I think there was some commotion. I'll be happy to talk to you. जी कोई सवाल? अच्छा जी, चलें. Let's move on. So now I'm going to talk a little bit about the band index, and I would like to give some more physical intuition to the band index. By the way, I hope all of you have a copy somehow of Stephen Simon's solid state, the Oxford Solid State Basics book. This one. If not, please get in touch with me. So this is a good reading resource for the parts of the course that I'm delving in these days. This is going to be my probably my last lecture on band theory. Then I'm going to move on to the tight binding model, in which the periodic potential, which we've taken to be a weak perturbation at the moment, is going to be replaced by a really strong perturbation, so that the electron really likes to sit close to the atom, the ionic cores. This is called the tight binding model, which the electron is tightly bound to the ionic core. What kind of dispersion relationships and bands do we get in that case? That's very important, because most of graphene-like and two-dimensional materials, their Hamiltonian comes out from the tight binding model. So that is going to be our next point of discussion. But band index. Let me talk a little bit about band index. You see, if I were to draw the reduced zone scheme, my zone boundaries pi by a minus pi by a 0. This is my lowest band, and I know that the higher band is, if I bring this back into the first Brillouin zone, I'll get this. Okay, so bring this back, I'll get the red band, the n equals 1 band. All right, so for the lowest band, or the n equals 0 band, I can, the wave function is similar to EIKX, Suppose we don't have any periodic potential, then this dispersion relationship is going to look like a parabola. Okay, so it's going to look exactly like this. What I'm going to draw over here, right? Okay, bands are going to be touching there. Without a periodic potential, of course, there is no gap. It's just a free electron. So this is what the band structure is going to look like. The bands are going to touch here at the zone boundaries. Okay. So look at the geometry of the band. The geometry of band is what captures most of the physical properties of these solids. So this is a really important concept. It's one of the most significant and cornerstone ideas of solid state. So for the lowest band, suppose my wave function is just EIKX. Okay. For the n equals 1 band, if uh, so if I look at this string over here, this string is can be brought back here. Okay, I can take the green part and stitch it back, because I'm moving by a reciprocal lattice vector. Okay, so what I could do, likewise, I could take this part and bring it back over here. I'm moving by a reciprocal lattice vector, and that's how I construct this second band in the first Brillouin zone. Now what I could do, if I consider this region here, a is greater than minus pi by a and is less than 0, then my wave function is really e I x. The wave function is defined by this green part here, this part, and this is given by x k plus 2 pi by a. Okay, so because I have to here in this region, the values of k are increased, they are incremented by 2 pi over a, and the green parts are identical because of the arbitrariness of k. So this becomes equal to eikx ei 2 pi x over a. So the wave function in this region, say this region, is given by this, and it's identical to the wave function in this region. Likewise, the wave function here is going to be identical to the wave function here. And what is this wave function? This wave function, as you can immediately tell, is defined in the region from 0 to pi by a. The wave function is given by eix. Now, what are the values of k in this region? They are simply k minus 2 pi by over a. So in this region, the values of k are equal to the values of k here. So I can subtract 2 pi over a from k and still get identical results. I get eikx e minus I 2 pi x over a. So I'm multiplying the plane wave by a function in which k is in which 2 pi over a is subtracted or added to k. That's what I'm doing here. In this, likewise, I can also take the points further out, and I can move these points by some multiple of 2 pi over a, and I can add or subtract to get all the dispersion relationships inside the first Brillouin zone. So inside the first Brillouin zone, if I look at the reduced zone scheme, uh, this is a plane wave and this is some periodic function in which I'm subtracting or adding by some multiple of 2 pi over a. That multiple could be 0, could be 1, minus 1, 2, 3. Therefore, I can identify this function by another periodic function x, and I can, of course, it depends upon what the k value is, but it is also characterized by another number. Let's call it n, which could be 1, 2, 3, 4, 5, and it tells us how many units of the reciprocal lattice vector do I need to translate the dispersion relationship to bring it back into the first Brillouin zone. So this n is called the band index. This is a new quantum number that is being introduced. And the wave function is characterized by quantum number k and its quantum number n. This n is called the band index. So the dispersion relationship is slotted out, it is bifurcated into these bands. Each band has a quantum number band index associated with it. N equals 0, n equals 1, n equals 2, and so on. And that n really tells us how many units of the reciprocal lattice vector does the wave function need to translate left or right to bring it back into the first Brillouin zone. All right. Any questions? Any discussion on this? Or so the wave function is now characterized by a k and is characterized by an n as well. And the block function can now be written as eik dotted with r. Uk is now characterized by another quantum number n. So this is our final form for a block function. All right. So any questions or any discussion, any confusions? The homeworks are going to clarify most of this. I'll try to post homework number 6 tonight or early morning tomorrow. जी कोई सवाल? Let's take a 1-minute break. All right, so I'm back. Uh, Now the question that can you hear me?
Yes, sir, can hear you.
Okay, 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 ठीक है. So now the question that I would like to ask, let me write down a question here. Excuse me. The question I'd like, how many K points exist inside a primitive unit cell in the reciprocal space? This is the question that I would like to pose. We know that in 1D, okay, please listen carefully. In 1D, the first Brillouin zone is like a unit cell, primitive unit cell in the reciprocal space. And that's repeated periodically to fill up the entire reciprocal lattice. So we have a unit cell in the reciprocal space, a primitive unit cell, right? That unit cell has a certain length, 2 pi over a. And within that unit cell, we had n, capital N k points, where n is the total number of unit cells in the real space that exist inside the solid. So bigger the solid in space, macroscopically for bigger solid, more K points inside the first Brillouin zone. The primitive unit cell in the reciprocal space with the caveat that it is symmetric around K equals 0 is called the first Brillouin zone. So the first Brillouin zone is nothing but the primitive unit cell in the reciprocal space, reciprocal lattice if you want to say, but it's symmetric around K equals 0. Uh, Let me first draw a few. Okay, I'll draw later, but let me first answer this question. How many K points exist inside the first Brillouin zone? We can easily answer this question in the following fashion. So if once again we can apply periodic boundary conditions called the Born-Von Karman boundary conditions, which tell us that psi r plus, so if I move along the x-axis, so let me draw the solid here. This is the real solid in the direct space. So there are, suppose n1 points, n1 translations as you go from one left end to the right end. And there are n2 translations, unit cell translations as you go from bottom to top. And there are n3 translations as you go from front to back. So n1, n2, n3 are the unit cell translations. Okay. Now, if I start here and go all the way around, I move, in other words, by n1a units. A is the unit cell length. I will get the original. This is a periodic boundary condition. Okay. Now this needs to be a vector. This is my A vector, my B vector, and my C vector. These are unit cell unit vectors in the direct space. Okay. Likewise, I can have the periodic boundary conditions along the y-axis and along the z-axis. Now, I also know what the Block theorem is. The Block theorem tells me that this thing here is going to be equal to psi r e I Now, what's the separation between R and this point? We have N1A units away, and I multiply this with K. This is going to give me psi R plus N1A, right? So this is from the Block theorem. You see the first form of the Block theorem? Let's go back. Let's go up. This is the first form of the Block theorem. Okay. So I'm just using this first form of the Block theorem, and I'm able to write down this this form. So if I look at this expression and I look at this expression, I would immediately recognize that this term has to be equal to 1. Likewise, I can immediately tell that my n1b dot k has to be equal to 1, my n3c dot k has to be equal to, all of these exponents have to be equal to 1, which means that this expression has to be equal to 2 pi times some integer, right? So this means that my k vectors, they have to be, they have to pick up certain values. They are not arbitrary. And what values could they pick up? Now, since k is a three-dimensional vector, now k has to be equal to some uh, multiple of 2 pi over a, some integer m1 over n1, plus, now this means that this is my, and I can put a unit vector with this. So let's put some unit vector. Let's call it E1 plus M2 2 pi over B E2 plus M3 N3 2 pi over C E3, where these unit vectors are in the direction of the reciprocal lattice vectors. Okay, because the k's are in the in the reciprocal space. So what this means is that, now how do we get this? So if I just had a one-dimensional solid, suppose I just had a one-dimensional solid in 1D, what would this problem look like? So that's easier to understand. In 1D, I will have the following: psi r can be replaced by x plus n number of unit cells a. This must equal psi x. But according to the Block theorem, this thing here equals psi x e I k n a, because the a vector and the reciprocal lattice vector, the k vectors are just along a line, so they are parallel to one another. So I don't need to take the dot product. So what this means is that k n a must equal to some integer times 2 pi. What this means that k must equal m over n 2 pi over a. But 2 pi over a is the length of the reciprocal lattice vector in 1D. Okay. So k, if I would like to write this in vector form, this becomes m over n, and this is a reciprocal lattice vector G. Okay. In 1D, this is simply a star. So now there is a vector relationship between the reciprocal lattice vectors and k. If I extend all of this to 3 dimensions, this is what I would get, which immediately indicates that my k vector is quantized according to m1 over n1 a star plus m2 over n2 star plus m3 over n3 c star. All right. So M1, M2, M3, they are integers. Okay, pause 0, 1, 2, 3, and so on. So what do I have now in three dimensions? In three dimensions, I have these k points. I go from one k point to another k point, so I can draw a grid. It's easier to draw a grid. The so on. So I can draw simplicity. Let's draw it like this. Draw a net here, another net, and all of these are connected vertically as well. Each of these points represents a point in k space. And how do you hop from one k point to another? If you hop along the kx direction by 1 unit, that means you're keeping m2 constant and m3 constant and incrementing m1 by 1 unit. That's how you hop along the k points in the x-axis. If you want to hop along the y-axis from one point to a neighboring point, you just increment m2 by 1 unit and keep m1 and m3 fixed. So each point in k space has a certain volume. Let So what is that volume going to be equal to? That volume is, let's call that volume of each point in k space, that is going to be equal to this length of this reciprocal lattice vector, this reciprocal lattice vector, this reciprocal lattice vector. You take the, so what you do is you move 1 unit in the direction of a star, and when you move 1 unit, how much have you moved? You have really moved a star dotted with n1. So if you increment m1 by 1 unit, this is the distance that you move, a star divided by n1, all of this. Then you move 1 unit along the ky axis. How much have you moved? You moved b star dotted with divided by n2. If you move 1 unit along the z axis, kz axis, you really covered this much. So this entire, you've covered some region in the k space, and the volume of that region is simply going to be equal to this expression. So you have three vectors, and you take the dot, the cross product, and the dot product with the third, you get the volume of this parallelepiped. Okay, so this is the volume of one point in k space. N is the total number of unit cells in the real space. So it depends upon how large the volume is. Okay, larger the size of the solid, larger will be n. So what, but a star dotted with b star crossed with c is just the volume of capital B of the unit cell in the reciprocal space. So it's the volume of the first Brillouin zone. So how many k points does the first Brillouin zone contain? It contains n k points. The first Brillouin zone contains n k points. We already proved that in 1D by simple calculation, and this also works in 3D. If you have a first Brillouin zone, the number of k points in that first Brillouin zone is going to be equal to the number of unit cells. All right. There are other ways to prove this as well, and one of my homework questions is going to talk about the other way. If I'm talking about a cubic system in which a, b, c, and they're all the same, then I could replace a dot b cross c with the volume of the unit cell. It's with just l cube, sorry, a cube, and so on. So the key idea is that the first Brillouin zone contains endpoints. Bigger the size of the solid, there will be more points in the first Brillouin zone, more K points. And remember that electrons have to be put into these into the K space. An electron lives on a K point. Two electrons can live on one K point because an electron can have a spin up or a spin down. So all of the electrons that are available and their energies can go up to the Fermi energy, they have to be populated into the K space. They have to be thrown into the K space while we respect all the physics that is the Pauli exclusion principle. And we're going to look at Fermi surfaces as well. The key idea, the first Brillouin zone contains n K points. And now how do we fill those uh, K points and up to what level are they filled? Is the first Brillouin zone completely packed or not? That determines the physical properties of the solid. So any more questions? And we can now start drawing some Brillouin zones.
यानी कि जो हर Brillouin zone है, it consists of contribution from each and every electron that we have filled. हर एक की थोड़ी थोड़ी contribution आ रही है और it's making a band sort of structure. Is that right?
So the first Brillouin zone depends on the Brillouin zones. They depend upon the geometry of the lattice, the symmetry of the lattice. The Brillouin zone scheme has the same symmetry as the lattice. In the midterm, there was a question. I gave you the example of a hexagonal direct lattice, and I asked you to find the reciprocal lattice. It turned out to be another hexagon. So the symmetry properties are preserved as we go from the direct lattice to the reciprocal lattice. So the idea is that the reciprocal lattice exists. You all know that the reciprocal lattice exists. It's not a mere mathematical construct. It helps in diffraction and so on. The first Brillouin zone is a certain region of that reciprocal lattice. Okay, and all the wave functions can be mapped into the first Brillouin zone. All the wave functions can have values of k's adjusted so that they lie within the first Brillouin zone. Their energy spectrum, however, it turns out to be sorted out into a band structure. So that's the key idea.
Okay, sir. ठीक है.
Okay,
Thank you.
so let's look at a few examples of conductivity in the next class, etc. So everything is going to be really clear, and you'll say, wow, just looking at the periodicities. So the Block theorem just involves the translational symmetry of the lattice. There's a translational operator, and you apply that translational operator, you get block functions which have a special kind, which are modulated plane waves. So everything is coming out because there is a lattice. Since there is a lattice, there is a reciprocal lattice. The reciprocal lattice has a certain region called the first Brillouin zone. Electrons go on to the K points. Electrons have certain K values, they have certain K vectors, and they have certain principal quantum numbers. So you have to fill up the first Brillouin zone like you're filling up atoms in a hydrogen, electrons in a hydrogen atom, depending on the energies and the N values. You fill up all of these electrons onto the available portfolio of bands and energies inside the first Brillouin zone, and you get your entire structure. And then that determines the optical properties, the electrical properties, and so on. The band theory, by the way, fails in certain cases. Remember that so far we're talking about electrons that do not talk to one another. These are independent electrons. The moment the electrons start talking to one another, you break down this requirement of independence. Then you have interacting electrons, and then this band theory just withers away to an extent. Then you have to resort to more complicated quantum field theoretical concepts, and you get different kinds of materials. Magnets, for example, I did a full course on magnetism. Magnetism relies on interaction. The only interaction that we consider while filling up these electron bands is the Pauli exclusion principle. But you also have the Coulomb interaction, you have the exchange interaction. Magnets don't really follow this band picture to a fair degree. There are other kinds of insulators, Mott insulators, superconductors. They don't follow this band theory because therein electrons are not independent. They are interacting with one another. Okay, so let me draw a Brillouin zone. And for simplicity, let me stick to 2D, two-dimensional lattices. So I'm going to draw a Brillouin zone and multiple Brillouin zones in 2D. So it's going to be easier to understand. So before I proceed, any questions? So in 2D, suppose I have a direct lattice which is square A, P. What is the reciprocal lattice going to look like? रेसिप्रोकल लैटिस कैसा होगा इसका? स्क्वायर लैटिस का, स्क्वायर डायरेक्ट लैटिस का
स्क्वायर ही होगा बट
स्क्वायर ही होगा, बिल्कुल. So let me draw the reciprocal lattice now. I take one point. Let's call this the k equals 0 point. Okay, I just choose an origin. Now this is my x axis, ky axis. Okay, and all of these solid dots represent k points. In fact, they don't represent k points. Sorry, this is a reciprocal lattice. These represent g points. These are reciprocal lattice vectors. All right. So this point here is, if this is k equals 0, this is a reciprocal lattice. So this point is 2 pi over a in the reciprocal space. This point is 0, 2 pi over a. The distance between 2 points on a straight line is equal to the length of the reciprocal lattice vector, 2 pi over a. This point here is minus 2 pi over a, 0. This point is minus 2 pi over a, 2 pi over a, and so on. Right? So remember that this is equal to g, which is equal to 2 pi over a. It's also equal to a star modulus. All right. Now, how do we draw the first Brillouin zone? The first Brillouin zone is drawn in the following fashion. There is a recipe. Now, if I were to take, suppose, let me first draw this unit cell here. Of course, this is primitive. It's a primitive unit cell in the K space. So it qualifies as the first Brillouin zone. All right. So, but the point is that the origin of this Brillouin zone is not at k equals 0. So what we could do, if I were to draw this unit cell here, this thing, then it's symmetrically disposed about the k equals 0 point. All right. This also qualifies as my first Brillouin zone. So I can take this first Brillouin zone and sweep this throughout the entire space to generate all the reciprocal lattice points. That's how we define a lattice, a primitive unit cell. You take the primitive unit cell and sweep it along kx, sweep it along ky, and you generate the entire reciprocal lattice. Okay? So the yellow box that I've drawn in the second instance represents the first Brillouin zone. Now, how can I draw that? There's a recipe to draw these Brillouin zones. So what I could do, I take my k vector, k equals 0 point. I look at my reciprocal lattice. I look at my neighboring reciprocal lattice points, which are closest to my point, to my origin. So here is one point, here is another point, here is another point, and here is another point. So this point has four neighbors, the closest neighbors of this point. And then what I do is I bisect each each of these vectors, each of these, of course this is a G vector. Each of the red lines that I've drawn is a reciprocal lattice vector. I bisect each one of them. Of course I bisect by planes. Now the area bounded by these bisectors is called the first Brillouin zone. And this kind of unit cell that I've drawn in this fashion, by looking at the bisecting planes of the reciprocal lattice vectors pointing to the closest neighboring points, is also called the Wigner-Seitz cell. So the first Brillouin zone is just the Wigner-Seitz cell in the reciprocal lattice. All right. So this green region represents the first Brillouin zone. Now what I could do next is I could take the next neighboring points and draw reciprocal lattice vectors to the next neighboring point. So the point that is next in distance from the k equals 0 point is this point. I have a point here, I have a point here, and I have a point here. So I draw reciprocal lattice vectors. And once again, I can draw bisectors of these vectors. So let me use a different color for the bisectors now. So I take this vector, I bisect. This is a bisecting plane. I take bisecting plane. I bisect this vector now. Take this first. The area inside circumscribed or inside these bisectors, but outside the first Brillouin zone, now corresponds to the second Brillouin zone. This area that I'm shading as brown is the second Brillouin zone. All right. So this is the second Brillouin zone. And what I could do, one thing that you can remember is that the first Brillouin zone contains capital N K points. The second Brillouin zone by geometry has the same size as the first Brillouin zone because because of the arbitrariness of K, you have to this needs to be true. So if I look at this region 1, I can translate it backward by a reciprocal lattice vector, translate it up, and I can get this region here. This vector can be brought back. This region can be brought back here. This region can be brought back here. This region can be brought back here. So I can take all the disconnected regions in the second Brillouin zone and stitch them back to form the first Brillouin zone. And the area of the second, overall area of the second Brillouin zone, which is now disconnected space region in the K space, is now exactly equal in size and area. It harbors the same number of points as the first Brillouin zone. Likewise, I can construct the third Brillouin zones and so on. So then I can now make vectors that point to the next neighboring points. The next neighboring points would be, for example, this point here. Take a bisector, and planes already exist for the from the previous discussion. So this point here becomes the third Brillouin zone. This point here becomes the third Brillouin zone. Likewise, this point here would become the third Brillouin zone. This point here, third Brillouin zone. Here, 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 here. So now these 8 disconnected regions, they can be moved by 2 units of the reciprocal lattice vector along kx and ky, and they can fall onto the first Brillouin zone. So in this fashion, I can construct the third Brillouin zone, the fourth Brillouin zone, and so on. The first Brillouin zone contains all the k points which are nearer to the origin than any reciprocal lattice vector point. So this is a kind of convoluted statement. Let me state again and slowly. The first Brillouin zone, by construction, you've seen that the first Brillouin zone contains those k points which are closer to the origin than any other reciprocal lattice point. You move away from the out of the first Brillouin zone, you have another reciprocal lattice point that is nearer to you than the origin. This is how we define the first Brillouin zone. And the nice thing is, by the way, this is also related to diffraction. If I, you remember the Bragg condition, and do you remember the, अभी मैं कह रहा था कि ये नजर ना लगे, इसको लगे. Do you remember the Bragg condition? And do you remember the vectorial form of the Bragg condition? The vectorial form of the Bragg condition, if I would like to recall, is k naught dotted with g is half g square. This is the Bragg condition. This means that if I am standing at the, so let me redraw this figure, it's become too cluttered now. This is the first Brillouin zone, the square lattice, k equals 0. Here I have point pi over a 0. Here I have 0 pi over a. Here I have minus pi over a 0. And here I have the point minus pi over a minus pi over a. These black bounded boxes form the zone boundaries. The zone boundaries occur in pairs, opposite pairs. So we have a zone boundary here and a zone boundary here, and a zone boundary here and a zone boundary here. So they occur in parallel pairs, these zone boundaries. And these parallel pairs are separated by reciprocal lattice vector length of the proper length, 2 pi over a. All right. And if I were to draw a vector to the zone boundary, got it? Let's call this vector k naught. My g vector is here, right? The plane is a bisector of the g vector. So if I take the dot product of k naught with g, okay, then that dot product is going to be half of the length of g, right? So g square, because you already have a g here and you need to normalize. So k naught becomes equal to g over the, so this expression becomes equal to half g naught g square. So all the points on this, on the zone boundaries, all of those points satisfy the Bragg condition, which means that these planes, these bounding planes of the first Brillouin zone are nothing but the Bragg planes. So if X-rays are coming into this particular direction, they are diffracted by the Bragg planes which form the zone boundaries. All right. And when you have this reflection from the Bragg planes, we've seen from the one dimensional example, and when we're discussing the time dependent perturbation theory, that energy gaps open up. And there's a reflected wave as well. And the incident wave interferes with the reflected wave to form a standing wave. And that is the Bragg condition. And certain energy values become disallowed at, at those zone boundaries. So at these k values, energy gaps appear. Now, this is a two-dimensional or a three-dimensional example, and it's hard to draw this. In the next class, I'll show you some real examples of some simulations for this. But energy gaps appear at the zone boundaries. Okay, so the energy becomes, in other words, the energy gaps at the zone boundaries, or you could say that the energy becomes discontinuous at the zone boundaries. The first Brillouin zone is symmetric about k equals 0. Opposite parallel planes separated by reciprocal lattice vector. Something which is slightly more complicated is that the first Brillouin zone has the same symmetry as the lattice. So in the next lecture, what we're going to do is we're going to put electrons into the first Brillouin zone, and we're going to look at some properties of metals primarily and some semiconductors based upon this understanding of the first Brillouin zone. The first Brillouin zone comes purely from the lattice. It's a construct in the reciprocal lattice space. Now electrons have to be fed into this into this reciprocal lattice. So an electron needs to be defined and fed in. So that is going to be the topic of our next lecture. So now I'll any questions before we finish this class?
Sir, can you go to that colorful zone picture that you draw?
This one? Yeah, Upar.
इससे ऊपर वाली सर. So sir, here are zone boundaries represent forbidden gaps, right?
In energy. At these
Gaps
zone
in
boundaries, there can be energy gaps if you have a periodic potential.
जरूरी नहीं है कि यहाँ पर gap होगा. There can be.
There can be. If your uh, if your perturbation is really really weak, the gaps are really small. If there's no perturbation, there's no gap. And if there's no gap, then these bands can touch. So if you look at this example over here, uh, here, you can see that these bands touch, right? You can have a scenario in which the bands touch as well. If you have a,
Okay.
now this scenario can be achieved. This is such a material is called a semi-metal. In graphene at 0 Kelvin, you have bands that touch one another. Okay. So you can have bands touching one another as well. You can have zero gaps as well. But having gaps is sometimes nice because you would like to either have insulating properties or you would like to have an optical response which is carefully engineered. So if you want to have an LED that is emitting blue light, you need to have a carefully constructed gap so that blue light can be emitted. Right? So you can have zero gaps as well. You can have bands touching one another.
Sir, is it like that graphite structure जिसमें हमारे पास एक डायरेक्शन में करंट फ्लो होता है और दूसरी डायरेक्शन में नहीं होता? Is it something like that या फिर उससे
वो
लिंक
जो
है?
एक डायरेक्शन में होता है वो that is called a helical spin transport. That is something more complicated. That involves other interactions, notably the spin orbit interactions. So that is also possible. It happens in two-dimensional topological insulators in which electron can only flow in one direction. So that's also possible. And all of this is described by band theory.
सर जो हमारे forbidden gaps हैं तो वो जो मैं आपसे जो आपने ड्रॉ किया उसमें पूछना चाह रहा था, तो फॉरबिडन गैस भी ओवरलैप कर सकते हैं आपस में, या वो नहीं करेंगे? क्योंकि
क्या मतलब? So there
सर
is a
डायग्राम
K.
से अगर मैं
So let me draw a diagram. So you can have a scenario of this kind. You can have a band structure of this kind. You can have really complicated band structures. Okay.
ठीक है, सही।
So this is the K. This is your energy. This is one band, say n equals 0 band. This is an n equals 1 band. So these band structures are determined in three-dimensional solids by simulations, by density functional theory, by some complicated techniques, augmented plane wave, and so on, pseudo potentials. So there is a way of determining these band diagrams for three-dimensional solids. Okay. So
ओके सर,
what
ठीक
is
है।
looking at in this class is the really simple stuff. Any more questions, my friends? All right. So thank you very much. Inshallah, see you on Thursday and look out for the homework. I'm going to update the website as well tomorrow. I'm going to post the solutions of the midterm as well. And let's see how things go. Inshallah. Ji, thank you very much. Or Khudafiz.
सर एक्सक्यूज मी,
जी जी।
सर मैंने आपसे वो थोड़ा सा डिस्कस करना था, जो प्रोजेक्ट आपने मुझे दिया होता बुक वाला। अगर आपके पास अभी फ्री टाइम हो, आई जस्ट नीड 5 minutes एट मैक्स।